Hello. Hello, good afternoon to you all and warm welcome from Kuala Lumpur to this ABU ASBU World DAB Joint Technical Workshop. This technical workshop is themed as DAB Plus Digital Radio Advanced Developments. We know that this is the last day, day 3 of the workshop. And we have interesting topics coming up, so I will not take much time. So at this moment, I will invite Dr. Les, as usual, to moderate the whole day's session, and then to move through the presentations today, and also to introduce some maybe housekeeping thing. Dr. Les will announce those things. Okay, without further ado, I will invite Dr. Les here on the screen. Dr. Les, yeah, over to you, please. Thank you.
Thank you, Sri, and welcome to everybody. I see people are streaming in now to join the webinar. Good stuff. We've had great attendance over the last few days, so hopefully today will be another exceptional day because we have exceptional speakers. I will just share my screen to go through the program. Today we are focused on building out the network. So we're going to talk a bit about DAB network design. Jerome Irigoyen from TDF will be giving us some good examples from his vast experience. And similarly, we will have a topic on DAB plus network implementation, where Hans Walter from DAB Italia and also the chairman of World DAB Spectrum and Network Implementation Committee will be giving us some examples from Italy. So that's all good stuff. That's focusing on networks, main networks. We will follow that by an update on small-scale DAB by Dr. Laurie Hallett, who will give us some ideas about how we can use DAB in smaller areas and maybe lower cost solutions. We'll follow that and finish off with a panel session on DAB measurements and monitoring, where we have an esteemed panel. We have Hans Walter back to talk about this topic as well. We have Christian Strom from Norway, from Telenor Norge in Norway, and Kenny Skillen, the head of engineering at Arqiva in the UK. So very eminent and experienced people to share their knowledge with you. And of course, we'll finish off with some Q&A. I encourage everybody to put the questions in. We will answer them one way or the other. Whether hopefully we can do them live. If not, we'll get back to you via email. So I think now at this point, let's kick it off with Jerome from TDF, focusing on multi-frequency and single-frequency network design principles. So Jerome, please share your screen and over to you. Thank you.
Thank you. I'm coming. Sorry. Let me. Sorry. That's okay. Is it okay? Hello, everybody. My name is Jerome. I'm working for TDF, and we are very involved in the DAB rollout in France. France is not a huge country, but we have more than 1,000 FM transmitter. And now we are moving to DAB. We have a different type of country I mean, different type of area in France. So I'll give you a short overview of how to design the network. I focus first on the field strengths and the basic, I must say, requirements for designing a network. Then we go to difference between the MFN and SFN network, and know a lot of technical broadcaster are asking what is the best solution to use, so I can give you some overview. First, talking about the field reference level. The starting point is to know the coverage, the requirements we have to understand, and we have to know which type of area you want to cover. Is it a big city, large city? Is it a countryside? And the second point is to define the receiver type you want to use. So basically, we have to check these 2 points as a starting point of designing. Designing the receiver type, there's a large type of receiver, from fixed reception, the handle for mobile reception, the mobile reception, which is very popular for radio, and also the portable receptions. More and more people are using some portable system to listen to the radio today. So we have to focus on this different type of receiver you want to use. Regarding the field strengths, there is a reference, an international reference today. You have in mind when you design your network for a mobile reception. Mobile reception means you use your reception in your car with an antenna rooftop, which have a very good reception level. So a field strength level under 54 dB microvolts is enough. And on the other side, if you want to have a indoor coverage, I mean deep coverage, deep indoor coverage, you need a high field strength design. If you want to go downtown, if you want to go in the basement of your building, so it goes to 75 dB microvolt per minute. So you see a large difference in the field strength design, depending on the receiver type and the country and area you want to cover. So this is a theoretical view, but with a World DAB, we make a survey to see what country, which field strength is used in each different country. This is a survey for European and Australia. We have different level from outdoor reception to indoor reception and dense urban. As you can see on the survey, We fix the location, the percentage of location needs, which is between 70 to 99%. As you can see on the figures, there's different reference for each country, difference for mobile reception and difference for indoor reception, which could be suburban, urban, or dense. As you can see, a lot of difference. For example, France is 54 dB microvolt for mobile reception, and UK is 44. You see, it's interesting. So this is some key figures you have in mind when you want to design your network. Second point of my presentation is a MFN network versus SFN network. So basically, DAB VHF network can be designed with SFN network or MFN network. Of course, it's an important and interesting facilities offered by DAB with a multi-subcarrier system. MFN means one frequency per transmitter. As you can see in the figure on the left, each transmitter has its own frequency, as it is on FM, I must say. Single frequency network means the frequency is the same for a number of transmitters. The difference between these two systems, I don't go in a technical and deep technical question, but the difference coming with the number of services you want to provide. It's a big difference. With an MFN network, you have a number of radio dedicated to the frequency. I mean, frequency 1, you have radio ABCD, and frequency 2, we have another list of radio, and frequency 3, another list of radio. I mean, you have a large landscape, a large possibility for radio and number of stations in this area. With SFN mode, of course, it's very interesting because you had only one frequency. It's very interesting in designing network. I mean, for frequency, for the regulator, I think it can optimize the spectrum using a SFN system. But as you can see, you have only one list of program per frequency. So 3 transmitter here should be the same contents of each transmitter, same contents. So I think it's a big difference, and you have to take in mind what you want to do, what you expect with your DAB network. Do you need a large number of stations? Do you need a reduced number of stations? So it's a good question that you can have when you design your network. This is a theoretical view, but I would like to talk about 2 use cases we have in France and could be installed in many countries. First example, here we have 3 cities which are 60 kilometers distance, and we design the network with the MFN option. Here you see on the north a city named Thionville, which is very close to Luxembourg, and Luxembourg, Belgium, and Germany. And as you can see in the picture, we have a coverage of the city with 1 transmitter. A second city located in the center here, which is Metz. They want to have 13 programs. So Thionville was 13 program, Metz 13 programs. And another one, which is on the south, another big city, which needs to have its 13 programs. So we have here an MFN system based on the 3 transmitters for 3 main cities. So it's interesting it's because we can have a lot of local stations, but it's a total of 39 stations on all this area, coverage for all these cities. We can have the same option with the SFN. What's happened with SFN? We set up the transmitter, the same transmitter, and we have a large coverage, but we have only 13 programs. A large coverage is very interesting because in this case, you see you can go from the north, I may say from Luxembourg area, and you go to the south with a high continuity with the same contents, but it's only 13. So here it's mobile reception, here it's indoor reception. So as you can see, MFN and SFN has a big difference concerning the number of programs. Another second use case, we have sometimes trouble using FM when you want to have a indoor coverage. Here an example, a city named Reims. You know Reims. It's a famous city for champagne. Everybody knows French champagne. So here we have a station located 10 kilometers away from Reims downtown. As you can see on the left on the pictures, there's a large coverage of the city with this transmitter. Unfortunately, when you see on the right, the indoor coverage, if you need indoor coverage, back to my first point of that presentation, if you need indoor coverage, the indoor coverage is not good. You can see that's a kind of hole, you see, downtown of the city. So if you add a local inside a local transmitter, in the city, so it's a real benefit for indoor reception, because you can cover inside the city. It's a benefit using SFN. So I must say we can design a network using a large design if you want to extend a coverage from several cities using SFN, and good to optimize the frequency management and the continuity. But we can use also SFN as to enforce the indoor coverage. So if I summarize here and fix some guideline how to design SFN, it's a multiplex must be the same, which is very important. You can't have different radios on the SFN network. So some multiplex, some services, some radio on the SFN zone. Of course, a high spectral efficiency for a large network. It's interesting for national networks, for example. Easy licenses process and SFN zone. It means you can add, when you have a license for a zone, you can add a lot of transmitters. So I depend on the rule of each country, but as I can see, it's easy for licenses. Opportunity to improve the indoor coverage, and technical network adjustment and monitoring to avoid interference, as you can see later in some presentation. Sometimes SFN networks, it's need to be designed with a lot of accuracy, honestly. MFN, a multiple frequency network, it's designed for multiple services. It should be compliant with the international coordination. I mean, when we change the frequency on the border, then it's easy to manage with your neighbor. Easy to design and manage, no constraints on adjustment and monitoring on the network. So it's interesting for local and regional network. And as I can show in my presentation, with MFN, inside the MFN, a large MFN network, you can add some enforced indoor coverage using SFN facilities. So I hope my presentation will be helpful for you, and thank you for your listening.
Thank you very much, Jerome. That's a very good explanation of the difference between single frequency and multi-frequency networks. In reality, when you build a network across a country, you'll end up using both of those techniques. They, as Jerome described, they have their own places and their own advantages. We're now going to turn to network implementation. We have Hans Walter from D'Abitalia to give us and share some of his experience with rolling out DAB in Italy. So Hans, please
Hello.
take the floor and share your screen. Thank you.
Yes, hello. Good evening to the people in Asia. Good morning to the people in Europe. I'm going to share my slides. My name is, for those who don't know me, my name is Hans Wolter, and I work for a network operator in Italy, which is called DAB Italia. It's a company which is owned by radio stations, and we provide the distribution service to them. We are currently operating a national DAB network with about 200 active transmitter sites. I have been asked to talk a little bit about high power versus low power transmitter sites. And so let's say I'll have 5 points I will touch in this description, in this presentation. And I must say I will build up a little bit on what Jérôme has already explained, which was very useful. I'll just illustrate the differences, some use cases, some new ideas, a little bit of history for what we have been doing in Italy. And then, let's say, I call it the truth is out there. It's, let's say, a rollout and some experiences we have gathered and which we really think you should build on in the future. So when we talk about high tower sites in Italy, where I come from, we usually think about sites like this. So very big towers on the top of the mountain, usually with a lot of antennas and big transmitters. Let's say, if you're maybe not from Italy, but from Germany, when you talk about high tower sites, you will look at a telecom tower like this, probably, or something similar. So these are, let's say, generally speaking, those sites where you have really big powers and very large coverage areas. When you talk about low power and low tower sites, in Italy, we might have something like this, which is a small transmission site near a city, where you have some TVs, some radio links, some internet providers on, and maybe also some FM. And we have here, of course, some DAB. It can also be really a small site, like a telecommunication tower in a village or in a city. So really something which is high, 10 meters high, where you have 4 or 5G sites and some Wi-Fi. So these, let's say, are generally speaking, the typical sites we think about when you talk about high power and low power sites. Of course, a high tower site is big. Usually we have a lot of antennas. So I say 4 or more antennas because you're looking to have a lot of gain. You will have a big transmitter in most of the cases. I say 1 kilowatt or more because actually for DAB, 1 kilowatt already is quite a lot, I must say, from our experience here. You will have a lot of ERP. It will be a site with a good or very big coverage, generally speaking. And it will be also a very expensive site because it will be remote. You will have a lot of hardware there. If you need to build redundancy, it will be very costly because you have already big site and big transmitters. Everything will be double the price. If you look at the low power and low tower situation, of course, it will be a smaller structure. You will have one antenna, maybe a few more, but not a lot of antennas. You will have a small transmitter. You will have a limited ERP, depending, of course, on the number of antennas, etc. You will have a limited coverage, of course. And you will have a cost which will, let's say, be market dependent, because in some cases it can be very low, the cost. In some cases, it might be a little bit more high because it will be a telecom site, and telecoms usually are a little bit more expensive. So when do you use, or when do we use in Italy, these kind of sites? High power, high tower sites were really those sites we used in the beginning. because when we started, now more than 10 years ago, it allowed us to have a big coverage very quickly, basically very cost efficient, in very short amount of time. When you will use a low power, low tower site, really when you need to fill the gaps in the coverage, when you need to add local coverage, when you really need to fill the gaps, small situations, and of course also when other sites are not available, because you have to fall back to other solutions. So there are a lot of different scenarios in this case. And in this context, while I was doing this presentation, I realized that most of the sites we are actually running are neither high power, high tower, and low power, low tower sites, but they fall in the middle. So I call them medium power, medium tower sites, because those are the sites which in our national DAB network fit in best. Also because when we build the network, we have to rely on existing sites, and existing sites basically, in most cases, allow such an implementation. So a medium power activation. And if you look at Italy, you see it's a very complex landscape. And maybe Christian, who will speak with me in the roundtable, can relate to this. We have a lot of water, we have a lot of mountains, but we also have a lot of flat areas in Italy. So here in the middle, for example, the Po plain is very flat and it's very long, and so it's of course very interesting. So we have, for example, in the north of Italy, a few high power, high tower sites which do all the flat areas. But we will see this will have some issues. Anyway, as I said, Italy has a very complex landscape, flat areas, lots of hills, a lot of mountains, islands. We have also high mountains next to the sea, which is really complex, a very, very long coastline, and a lot of warm water around Italy, which of course has a lot of propagation effects. And we have many, many neighbors. We have at least 14 neighboring countries with whom we have to coordinate the frequencies. And that is really a problem. And just to look at the history we had in Italy for DAB, when we started, which was, let's say at the end of 2010, the situation for DAB was not really certain. DAB Plus was still very new. Car receivers were really scarce. In Italy, there was a very strong FM landscape, and so digital radio was only considered to be a cost. There was no real frequency plan made by the regulator, and for some people, DAB Plus was already an old technology. So we had to be very quick, and therefore, as I said before, also we went to this high power, high tower sites at the beginning to have a very extensive coverage. This is what we got. After a couple of years, basically, we had a really good highway coverage, and this was very important for the car industry because this gave them the opportunity to see that there was coverage and that there was a need to have DAB Plus receivers in the car. But we also had, let's say, a limited indoor service because, of course, these high power, high tower sites usually are not in the cities, but far away on the top of the mountain, as I said, so not really. So after, let's say, the beginning of our rollout, we basically stopped building high power, high tower sites and went to the medium sites because there was not the availability of the sites. There was not the cover, they were very expensive. We needed to have a more detailed coverage, and we needed to defend the SFN because one thing is talking about the effectiveness of the site, but when you look at SFN, and Jerome has touched on this very well, things get very complex. So looking at what we are going to do in the future is we will really not do any high tower sites anymore. We will do medium power and medium tower sites. And we will introduce what I call high power, low tower sites. So small sites, but with high power to give a good indoor service in urban areas, which is very, very important. And of course, we will build also low power, low tower sites to fill gaps in some areas. But let's say it will be more on having more important towers. But if you look at this, it's only really half of the story, because if you look at DAB+, the most important characteristic of DAB+, from our point of view, as a network operator, as a broadcaster, is really the single frequency network. It's a very, very, very powerful feature, which allows really exceptional results, but it is also a weak point if it is not well managed. And in this context, high power, high tower sites are not suited very well. And we have found this, let's say, out over time, because really we did some of the planning at the beginning, but then we realized that propagation effects and other things have not been really simulated correctly. And we find that these sites don't work in SFNs, but they might work if you have a smaller SFN, or if you have an MFN or a KSFN. So if you have in one country maybe a single frequency network divided by areas. The other problem is, of course, let's say the frequency planning, both at national and at international level for DAB, which limit the use of this kind of sites. Because if you use high power, high tower sites, the reuse of the frequency will be difficult, and the cross-border coordination is very complex. If you don't have neighbors, or if you have a little number of neighbors, it might be easy. If you have 14 countries to coordinate with, it becomes very, very big. This is, for example, a scenario where I see single frequency interference in Italy. And we have them over the Adriatic Sea. We have them inland. We have them all over the Ionian Sea. We have them over the Tyrrhenian Sea. So we have really a very complex scenario. And we have to deal with this, adjusting the offset, etc. But this is, let's say, a very technical aspect. And this really limits for us the use of this kind of sites. Even here on the plains, if we put in operation a transmitter on the north of the Alps, this will arrive on the south of the Po Plain, but we cannot put into operation another site here because it will interfere somewhere else. So it's really complex. And therefore, we really look for smaller sites. Another point is, if you go to medium power, and low power, low tower sites, you will have a more resilient network, because having a really redundant high power, high tower site will become very, very expensive, because you can have two transmitters, you can have two antenna systems. But really, if you are on the top of the mountain, the only really real existing redundancy is having a second site, because if the tower gets damaged by lightning or by something else, you need a physical second site, and this becomes very, very expensive. And when this site goes off air, you will have a big hole in your network. If you go to smaller sites, these become more resilient, because even if a small cell, like in the mobile phone networks, goes off air, you will have only a limited area which is not covered. And if you plan your network well, probably you'll have a lot of overlapping coverage areas anyway. And this is really, really very, very important. And we see this in real life in Italy. So I have failures every day. We have 200 sites, we have bad weather. And I really get very few complaints because in many areas we have transmitters which overlap in the single frequency network. And this is makes it a very resilient network. If you have a city which is covered by 3 or 4 transmitters, if one fails, you still have 2 or 3 transmitters working on the city. You will have a limited indoor coverage maybe, but there will not be a big gap in the coverage. So smaller sites provide, in our opinion, in our experience, a more resilient network. And here we come basically to the end of the presentation. This is what I think really. We should move from high power, high towers and low power, low tower sites to the opposite. So low power, high power sites and high power, low tower sites. One for the cities and the others for those transmitter sites where you are on the top of the mountain. On the top of the mountains, you need to go down with the power because otherwise you will not be able to manage your single frequency networks. If you are down on the floor near the cities, you can go up in the power because then you can achieve a good indoor coverage. So, as I said before, from our perspective, which is, of course, a view from a particular territory, but use as few high power, high tower sites as possible. Go high power, low towers, if possible, because this is probably the best solution. Try to plan for a comprehensive network from day one, which is very difficult because you will never know exactly if all the sites you put in your network plan are available, if the cost is acceptable, if they have the connectivity, the possibility to be built, the authorizations, etc. If something goes wrong, don't be afraid to change it. And if possible, use single frequency networks as much as possible, because you will have a very good coverage because it integrates, as Jerome has also explained. And also because what we see, especially in cars, the switching from one frequency to another is not always so easy. And therefore, the less you force receivers to switch, the less issues you will have. So thank you very much for your attention. Yesterday, I was changing a transmitter at this site, and this is a low power, high tower site. So it's something really in the middle. Thank you very much. And back to you, Les.
Thank you very much, Hans. That is very interesting to hear the Walter law. It really is one of those things that you only learn through experience. You know, the obvious way is high power, high tower, filled with low power, low tower infills, and that's certainly what we have in Australia. But we're yet to build out our regional network, and I expect that if high power, high tower sites are used for that in Australia, it will have the same issue in terms of interference between different license areas. So using the same frequency, of course. Very interesting. Yeah. Thank you very much. We're going to move to something a little bit smaller now. And we have Dr. Laurie Hallett to talk to us about small-scale DAB and how that is being rolled out across the UK. So, Laurie, please, over to you and please share your screen. Thanks.
Thank you, Les. Good morning, good afternoon, good evening, everyone, wherever you might be. Pleasure to be with you. I'll just share my screen. So I'm here to talk to you about the rollout of small-scale DAB in the United Kingdom. And I'm just going to lose the web chat screen, which has just appeared on top of my screen. So my name's Dr. Laurie Hallett. I have been the Operations Director at Future Digital Norfolk since 2015. My background is as a regulator, so don't hiss and boo too much. Now, if I can get my screen to go up and down, which for some reason it's not doing, just bear with me. Right. So Future Digital Norfolk Limited is a not-for-profit company. We come out of the community radio sector. Myself and my co-directors are also co-directors of the local community radio service. We set up the digital platform as a separate entity, partly so that it was protected from any issues that might occur at the community radio station, and also so that the community radio station would not be affected if anything happened to the digital platform. We launched our long-term services in Norwich last year, and we serve about a third of the county of Norfolk. It's about 300,000 people in our coverage area, adults above the age of 15. We carry just under 20 services, mostly in DAB+ at 48 kilobits per second in stereo, which we think is about the best compromise, but other people will have different views. But we also carry 2 services in the legacy DAB mode, just because that is what the client requested. Outside the operation of the actual multiplex, we also provide support for prospective other not-for-profit DAB operators. So we started as a single transmitter service in the city of Norwich in the summer of 2015. It was one of 10 trial licenses granted, and it was originally intended to operate for a few months. However, it took until last year for us to get the full-time license. And we based that operation on open source software and hardware, mostly provided by Ofcom, the UK regulator. So that's an indication of the coverage achieved by one transmitter. About 200,000 adults from a single transmitter located close to the centre of the city. We use effectively tower block sites or high office building sites. So our transmitter is on a 12-storey tower block with a high gain omnidirectional collinear antenna. That's our coverage now. It's a bit difficult to compare the two because they were done on different software, but it is slightly wider. It's at the moment a 2-transmitter single frequency network, and it serves about 300,000 people, adults over the age of 15. So let's have a look at the drivers of small scale DAB and where they fit into the wider DAB ecosystem. So Ofcom was interested in supporting the sector and rolling out the availability of DAB to broadcasters who couldn't gain access on some of the larger regional and local multiplexes. There were also issues around competition policies to try to diversify the ownership and operation of the infrastructure. It was also designed to try to accommodate different and diverse economic models. So going not just to the purely commercial or public service, but also allowing new entrants such as Future Digital Norfolk, who provide this on a not-for-profit basis to try to develop services for people in our local community area. I think in terms of the technicalities, it's important to remember that the frequency resources used for small-scale DAB are available for that use at low power, but they would not be available because of international clearance issues and reuse issues and single frequency network issues if they were to be used at higher power. And essentially these services, these transmitters, these multiplexes support community-based and hyperlocal services, some of which are commercial. In this practicalities, we were worried about, as the regulator, the issue of digital migration capacity. Could we find space for all the small FM stations on the existing DAB multiplexes? Answer, no. And even if we could, what would be the access and cost limitations? So the idea was to bring in a new form of smaller scale DAB to accommodate a greater number of broadcasters, to enhance competition and provide more choice for the listener. So as I say, that's really looking at the lack of a digital migration path, the fear of what we call in the UK the analog backwater. Everyone else moves to DAB and you've got services left on FM with very few listeners. Encouraging those new entrants. There was a lot of interest in open source systems, and they are indeed still used to a certain extent, as I'll explain later. and using those DAB blocks, which would not otherwise be available for high power operations. And the experiments in the trial services were the first ones to use DAB Plus in the UK. And it's very interesting to see how quickly, once that was proven by the trial services such as ours in Norwich, how quickly that was taken up by the core established infrastructure of DAB broadcasting. So let's have a look at it. That's, for my sins, that's me there showing people one of our small transmitter installations. And as you can see, it's very small. Open source technologies are used. Our distribution of signals from the contributing stations to the multiplex are done over the internet, domestic internet, if you will. We're very small service areas, as you could see from the previous maps, and using lower power transmitters. So our transmitter there is a 150 watt transmitter into a collinear, which provides a radiated power of approximately 200 watts. And as I say, it's rooftops and private masts that are used, and we're operating on, if you like, a non-standard business model. So what were the impacts of the small-scale DAB experiment? Well, it definitely demonstrated the effectiveness of the open source DAB resources that are available. And it also allowed that open source model to develop its single frequency network DAB resources, which in 2015 were limited and are now well developed. It proved the reliability of low-cost internet contribution feeds. We did an analysis in 2016 of the uptime reliability of our connectivity compared with existing established broadcasters, and basically we were exactly the same. In some cases a little better, in some cases a little worse, but the internet contribution feeds were not intrinsically a problem. It did encourage the development of next generation commercial equipment. So in our current system, we do use some commercial equipment, and we're very pleased to be able to use that, as it simplifies operational activities. And I think underpinning that, it facilitated revisions of regulatory policy, both on the technical side and the content side. So the regulation of DAB has changed as a result of the small scale experiment. I won't go through this in any detail because you've all seen it before, but essentially it's a very simple basic block system block diagram of the service providers each sending their material via the cloud into a multiplexer, into a software defined radio, amplified through an amplifier, filtered to make sure it doesn't cause problems, and then going to the transmitter. That's another display of it, but this one I think shows that we really take the approach of building in resilience. So our individual program services, as they're delivered, they will deliver via one internet feed, but always with a backup where that can be provided. That goes to two separate cloud servers, which are geographically diverse. So if one set of connectivity fails, another comes up. There are two feeds from those cloud servers to the transmitter sites, plural. So each site has two inputs. And in fact, there's a microwave link between the two sites, so that should one site lose all its connectivity, it can still be fed off the other. That goes into the ODR DAB MUX, into the modulator, into the software defined radio, through the power amplifier and filter, and to the antenna. And I think that's the key point. When you're looking at the operational approach for small scale DAB, you need to look at your resources, your internal resources, and your capability of bringing in external resources. What is your capital capability? How can you keep your recurrent costs down? And what are the skills that you have in-house that may offset the need to spend recurrent expense on external experts to build up your system and keep it reliable? And we've worked very hard to make sure that we reduce all single points of failure. Our transmitter coverage in an SFN has a lot of overlap. And when it's fully rolled out, if one transmitter fails, I doubt that only a very small percentage of people will ever notice any different. We make sure that our data feeds and inputs are multiplied, so inputs to the transmitters are multiple and inputs from our contributing stations are multiple. We've also implemented a lot of secure remote access and control so that we don't have to go to the transmitter sites wherever possible. And I think this is a key point to bear in mind outside the technicalities, which is because we have a lot of separate multi-service providers, then we are not dependent on one external provider to be paying the fees for carriage. Should we lose one service provider, it's a small impact on our operational income, and so we're not dependent on one major broadcaster effectively underpinning our income. We've tried to make sure that we can be responsive when things go wrong, as indeed they always do, and that is through standardized technical equipment and through broadcast-ready super spares, which we can take to a site. And we do that in close collaboration with other multiplex operators. I'm not going to go through this in any great detail because that would take too much time, but I think the key point is that we have evolved that signal path over the last 8 years or so. We can take pushed feeds from individual transmission providers, or we can pull them. We make sure that we can insert dynamic label text and pictures, etc., remotely should they fail. And we have moved away from streaming to predefined IP addresses, partly for security, but partly for flexibility. And now everything goes through fully qualified domain names, so we can make changes to the system without anyone else at the service provider level having to make any changes for us. I think I'm not going to go through this in a great deal of detail, but I think the key point here is that we have worked very hard to make sure that we build in that resilience and that we are able to make sure that Norwich is a if you like a fairly medieval city. It has some quite small streets in the centre of it, so we do need high field strength in the centre of town. So our transmitters are kind of located in a ring around the site, around the city, and that means that the coverage of the dense population in the centre of the city is greatly enhanced over when we had a single transmitter. Just quickly to finish up, monitoring, which is very, very important. We use a Gatesair transmitter for our County Hall site, and that gives us a lot of information. We know what's going on, and we can make changes to it should we need. But we also monitor using some standalone monitoring, which is located at different points around the city. We've used this product from Innovonics for since the outset, really, in 2015-16. We're just about to upgrade it to their later model. The great thing about this is that we can provide access to individual stations operating on the multiplex. They have no control over the multiplex because it's not connected to the multiplex directly, but they can see and hear what's being broadcast on their service. We also use Quirks, which is a very useful system for making sure that our single frequency network is timed up correctly. We use a French system, which we like for monitoring, again, because we can provide it to the individual station operators, digital bit rate. And I think that's where I will stop. Thank you very much, and I'm happy to answer questions later on.
Thank you very much, Laurie. It really seems that small-scale DAB is taking a lot of the same precautions that commercial and public service broadcasters, main broadcasters are using too. I was very encouraged to see your use of multiple different types of redundancy there to make sure that you get your coverage and consistently. Okay, we can do a few questions later, but I think now we're right on time for our panel session. Now, the panel session today is focusing on measurements and monitoring across a variety of different situations. So we've got 3 short presentations from different countries, and I think we'll go through the order as in the program. So that would be over to you first, Hans, for your discussion on DAB measurements and monitoring, please.
Okay. Hello, can you see the slides? I hope so. Okay, so very quickly, because I will not elaborate too much on this. I think it's good when we have a little bit of discussion on this. As I said also in the previous presentation, when we started over 10 years ago, what we really did was, and at that time it was not easy to have connectivity on transmitter sites, or not on all in Italy, but we insisted to have all DAB transmitters online available. So at the beginning we had 15 sites, but they all had IP connectivity, and this allowed us really to monitor very precisely what was happening. And we had these wonderful old transmitters with a lot of functions which needed a Java of a certain version and a certain operating system and a certain browser. It was very complicated, very slow, and we really had to monitor everything manually. So we had to open up the different websites or the browsers to see what was happening. And basically we had no real alarms. It was very limited. And therefore, the first step we did was to implement a network monitoring system, which we still use, which is very simple, but it is efficient because basically you will have some dots on the map. It will read a certain number of parameters via SNMP. If you lose connectivity, you will have a blue dot. If there will be some value out of range, you will have an alarm. And if it's green, it's okay. This allows us also to have a reporting. So we really can check with this system how much uptime we have on the sites. But over the time, we really noted that we needed much more data points than just power, temperature, reflected power, satellite level, signal input level, etc. Because, and here we come back to what we said before, and also what will Christian say later. When you are operating inside a single frequency network, you have to have a very great detail of information on your machine. And so now we have moved, let's say, from this kind of operation system to something different, which is based on an open source platform, which is Zabbix, and where we basically monitor, and you can see it here on the right side, for example, for a Gates transmitter, we monitor over 50 data points of a transmitter. So everything. We monitor the software version, we monitor the accesses, we monitor all the temperatures, all the values, and that's very important. We monitor all those data points which are referred to the delays, to the timing. And this inside an SFN is very important. And let's say a more complex system allows you also to have a different kind of alert. So on the old system, we just had a red flag, so there was a problem. And here in this system, we really can create a series of alarms, warnings, etc., which allow us to have a much more precise identification of the issues. And this is really, for example, this is a screenshot from last week, basically. So you see what all the transmitters which are in the system. There are all the transmitters which are not all still in the system. And we have a lot of alarms popping up and going down because you have issues on not hitless inputs, of high temperatures. In the last weeks in Italy, we had temperatures over 40 degrees in some areas, so the transmitter stations were becoming very hot. We had a lot of thunderstorms, and so we have really a lot of stuff going on. So just from our experience, what we can say is, of course, it is important to monitor the network, but it is very important. You have to invest a lot into the monitoring, because the more complex the network becomes, the more important it is that it's monitored. All sites need to have IP connectivity. The most big problem we have is really to have a very precise identification of the issues and to be able to isolate fake information. What we see, for example, sometimes is you have a modulator which blocks, and he says, no, I'm okay, everything is okay, my timing is correct, and in truth, it's getting out of SFN. So you need also to have test receivers on the field which can monitor the SFN. Otherwise, you really risk a lot of problems. And as I said, you need to program your system very well and create also automatic fallback scenarios. And we are working on this, for example, to limit the propagation effect. So in the summer, when temperatures go very high, and we see that on some test receivers, we have signals popping up and out of the guard interval, we can put down or limit the power of those transmitters which are affected more by propagation. So let's say it's a regulation for special events, let's say, in a certain. And this is very important because when you have a lot of transmitters on air, you need really to fine tune everything. And of course, you really need to know your network very well. And therefore, really, the more you monitor, the more data points you get, the better. So that was, let's say, my introduction. I hope this helps to start the discussion. Thank you.
Thanks, Hans. It's really very interesting. The science, you might say, of monitoring digital broadcasting is increasing all the time, and I think you're making some really good contributions there. I look forward to some of the other ideas we've spoken about in the future. So let's move on. Now let's go to Christian Strom from Telenor Norge in Norway to speak about how they manage their network in a very mountainous country. So over to you, please, Christian.
Thank you. I will then share the presentation. I hope you see it now. I can't see it, but I guess you all see my presentation. Yes, do you do that? Les, can you confirm?
Yeah, all good.
Yes.
All good.
Okay, fine. Good afternoon to everyone. My name is Christian Strom. I work for Telenor. We are the operator.
Recording in progress.
I will tell you a little bit about SFN and how it works, because you have several transmitters and they're all transmitting on the same frequency. So a receiver will then receive all the three signals at the same time. I'm trying to demonstrate this by having these lines indicating the different
sorry,
phases.
Christian. Sorry, Christian. We
Yes.
lost your slide. Can you again share your slide from the beginning?
Okay, I'll do that.
Okay,
Yes.
thank you. Yeah, fine. Thank you. Please go ahead.
Okay, good. So as I said, then I'm trying here to explain how SFN works by having these three lines indicating the DAB signals, different colors.
May I interrupt you? I think we have seen your presenter view, not the second screen. Could you please share the second screen?
Okay.
Yeah,
Yes, I think
yeah,
I was doing that.
right. Actually, previously we saw the two slides upcoming and the present slide things in the on the presenter view. So now,
Okay, we'll try again.
right. Okay, great. Thank you. Right. Please go
Okay,
ahead.
now you see them. I'm sorry about this. So as I said, I'm trying to explain how SFN works, and now you see these three lines indicating the different DAB signals, the colors representing the different phases. So if we have a transmitter which is in the middle of the three transmitters, they will reach the receiver at the same time, and the two signals or three signals are received at the same time. If we move the receiver so that it's not equal distance to all the transmitters, the signals will be received at different times. And this is where you have an interference between the two signals. Now transmission will stop. It's not possible to decode the signal. That's why we have in DAB introduced this guard interval, which is 246 microseconds, indicating or approximately 75 kilometers difference in transmitter distance. So now when the decoder is decoding the signal, it's seeing the two signals, the two symbols are the same, so the receiver is happy. If I move the receiver further away, increase the power of transmitter 2, because the distance is now bigger than the 75 kilometers, the signals is received at a time difference which is greater than the guard interval, and we now have a problem. Now transmission is no longer possible. This is what we call the SFN problem. This can be avoided or reduced by delaying some of the transmitters, which are indicating now. I'm delaying the signals from transmitter 1 and 3. Now, as you see, now the signals are being received at this receiver point with a time difference less than the guard interval. So now it works. Let's have a look at some of the transmitters we have in Norway. It's a lot of transmitters, and I've here done a calculation where the red color indicates areas where we will have self-interference. And this is the network as we've built and operating at the moment. And as you can see, there are some areas where you may expect some self-interference. We try to move this by using the delay times. This is a big puzzle you have to do to make sure that you try and move these areas into places where nobody lives or wants to listen. This is what it looks like if there was no delay. It's a bit bigger. And if you look at this blue square, you have the transmitter at Kongsberg, which is a long way away, more than 90 kilometers, and it's line of sight. So this, because of quite high power, would introduce self-interference. But by delaying the transmitter at Sarpsborg, it will reduce the problem, and it's quite okay. So SFN errors is then if one transmitter has the timing issue wrong. That means that it will transmit the signals not when it's supposed to, but at the wrong time, and then you will have some bigger problems with SFN. If I now imagine that this transmitter site is getting the timing wrong, it will then output signals which will make self-interference. Listeners will call in and complain that the transmitter must be turned off because they can no longer receive any DAB signals or DAB audio. But it's not the case, because close to the transmitter, the signal will be okay. And this is what's confusing the service engineers. When they're told to go out and look for an error at a transmitter site, and they go close to it and everything seems to be okay. You need to go out in the field and look at what we say the impulse response or the echo pattern. So we use some measuring bands, and here I'm showing you the display of an instrument. You can see here that the timing of these transmitters are all within the 246 microseconds guard interval. So this is okay. Here is another issue where we have one of the transmitters which are suddenly being received outside the guard interval. And now you have a problem. You cannot decode with the normal radio. You cannot get the audio. But if you have put up and identified with the transmitter ID, you can identify which transmitter is causing the problem. So they are very difficult to detect. At least it's almost impossible to detect it at the transmitter site. Listeners will complain and call you. And this is a little tip that if you suspect one transmitter has an SFN error, you can turn it off for a short while the person who's complaining is still on the phone, and hear with them if it's now okay. Very often, this will fix the problem by turning off some of the transmitters, and if we reboot them, it will sometimes fix the problem, and then you have a happy customer again. Everybody can listen to DAB in this area. So that was a short talk about SFN problems. So thank you for listening.
Thank you very much, Christian. There's some real learnings from that, I think. And you know, I think this and also Hans' presentation demonstrate that while single frequency networks are really valuable, in terms of coverage and spectral efficiency, you really need to know how to design them correctly and really need to understand propagation and characteristics and to actually monitor them correctly to make sure that your listeners don't have a bad experience. Okay, we're going to move on. One more, a little presentation from Kenny Skillen, Head of Engineering at Arqiva in the UK. So Kenny, please share some of your wisdom and your screen. Thanks.
Thanks so much, Les. Thank you very much. Hello, everybody, wherever you may be. I'll just try and share my screen with you. Okay, hopefully that is now coming through. Can you see that slide?
Yeah,
Yes,
that's all good. That's all good, Kenny. Thanks.
Great. Thanks so much. So good morning, everybody. My name is Kenny. I work for Arqiva. We are a broadcast service provider within the UK, and we also provide utilities smart metering services as well. We provide a lot of DAB services in the UK. And today I'm just going to take you through a few slides just around actually our approach to network management and some of the monitoring solutions that we have across our networks. So we have quite a large number, like many of the other speakers as well. We have just over 1,200 transmitter systems across the UK for various different customers and clients, and we manage just over 60 different multiplex ensembles from a lot of different locations across the UK. We're bringing in a lot of studio sources, over 350, and we're taking them to various different places, processing them, and then ultimately broadcasting them from just over 500 sites across the UK. Pretty much all our networks operate in an SFN mode across the UK, and they are monitored from our network operations centre, which we have in the north of England. So we have staff there running 24 hours a day, 7 days a week, providing real-time monitoring for those services. And that's our service management team, if you will, and we have two kind of main processes around that we can manage. One is around incident management, one is around problem management. I think with the size of the networks and the data that we have, and Christian mentioning actually how important it is to bring a lot of that data back in as well. There's a lot of data to try and contend with, and how do you actually can work out what a real service issue and what is not. So we have tiered framework for management with tier 1, where we have our network operations center, and we have our staff 24/7. They're there around the clock, and they're monitoring events across the network, and they're trying to resolve incidents and events as they take place. If they cannot resolve them, then we will likely dispatch some of our field teams, and they'll go out around the country and they'll try and rectify that. And if that's not successful, then we would move to what we call a tier 3 team, which is where our subject matter experts are in DAB transmission, of DAB, MOX, and coding, and those teams would support those incidents to resolve that. What we tend to do is we take all our incidents through into what we call a problem management routine, where we will look at the root cause of those incidents and then try and put in place any learnings or actions to try and avoid.
Yeah. Hello, Kenny. Hello, excuse me.
Hi there.
Yeah, I believe there is a network problem when you share the screen, so your audio is interrupting. Maybe we can share from our side. Yeah.
Okay.
Can you stop sharing? Yeah, we'll share from our side, and then you just move ahead. Just say next. We'll move.
Okay, I will do.
Yeah,
okay, I've stopped sharing.
Yeah, just a second. Right. Yeah. Are you able to see the screen now?
Yeah. Thank you very much.
Yeah. Please go ahead.
Shall we move on to the next? Yeah, next slide, please. Sri, thank you so much. Okay. So how do we manage the health of those services at scale then? So there's two key aspects to that. One, we've mentioned previously, I think Hans has mentioned the importance of that installation and commissioning, where we'll look at those systems, we will test them on site, we will check the functionality of them, and we'll test the management connections back to the main operations center. We'll also be doing timing checks at that commissioning point. And then as we move into the in-life operation of that service, there are two aspects of that management service. One is reactive and one is proactive. So our reactive maintenance monitoring is around network operation center, and they're trying to do time corrective actions to resolve and dispatch staff to. We also do periodic checks where we're going to do proactive maintenance. We will do regulatory checks, function checks, time check, and even basic things, just ensuring that the cooling is good, the ventilation is good, systems are not overheating, making sure they're working, which also helps their reliability as well. And our customers on that, actually, we have availability, we have to reach as well. Next slide, please, Rick.
Sorry to interrupt, Kenny. You're still having a lot of glitches on your audio. I'm wondering if you could maybe stop your video feed to give priority to your audio. Thanks.
Yes, I can. Okay, can you still hear me?
That's good. That's good. That sounds better.
Great. Thank you so much. So here's an example on the screen of one of our management interface screens. And what we have is we have a graphical representation of our transmission site here. And this is replicating the architecture of an end-to-end system. So you can see on the left-hand side there are some satellite feeds coming in, and then they move into the exciters, through into a changeover unit and an amplifier. And that is the display that our network operators will see. So they get this abstracted graphical view, which summarizes the data points that they will monitor. And when you're trying to manage 1,200 transmitter systems, that simplified view does help, because a more management system is able to aggregate that data and prioritize which events are higher priority. If you look closer on the screen, you'll see some little green kind of dots, and that's the new status symbol of those particular metrics and parameters. And we're monitoring the exciter health there, and crucially, we're also looking at the timing of the transmission, as well as getting some real-time metrics on the amplifier system as well. Next slide, please, Rick. Okay, I think that's moved on. So timing is a really, really important aspect of the success of DAB. And across some of our services that we provide for customers, we have hundreds of transmitters operating on the same frequency. So how do we determine that those transmitters are working at the right frequency and are timed correctly? We have an on-site box which we've developed called a transmission timing monitor, which looks at framing points within the ETI ensemble data. And what we're able to do is to determine against a set of reference values where those boundary points for those frames within the ensemble should take place. We then bring that information back to the network operations center. And so that screen on the left-hand side that you can see is a list of all transmitter sites, and crucially, their comparative timing between each other. And what I've highlighted here in that red ellipse there is the fact that these are the deltas between their expected value and their real value, and you can see across the network the values only differ within a few seconds. Now, that data is determined by not just the distribution path, the transmitter type, the exciter type. So we normalize for different types of infrastructure, which gives us that that consistent value that we can display on screen. And really importantly, at a glance, an operator is able to see that the timing is good or the timing is bad. Next slide, please, would you to summarize? So to sum up, I think when we think about our DAB services that we provide, we do try and have an end-to-end service management wrap, end-to-end, so from MUX all the way through distribution and into transmission, and we like to do that in a graphical way to provide that simple interface for the operators. We like to group and display timing information together for networks, so that at a glance we can see the network is good. So that graphic on the right hand side there is just giving you an idea that across the network the sites are in co-timed correctly. We do use systems trigger thresholds. We've heard from the speakers already today, and trust those systems to give you that information, and do take advantage of automatic corrective switching within those systems as well. And with that data that you learn from your incidents, what are those root causes, getting underneath of those and trying to avoid repeats of those incidents as well as gathering data and bring as much data down in that story that allows you to debug and post-incident analysis, but providing that simplified 24/7 view for operators. So I hope that's been of use for you today. Thank you very much. And with that, I'll hand back to Les.
Thank you very much, Kenny. Again, a very interesting presentation. We've got a little bit of time left before we have our summing up. There is quite a few questions in the Q&A. We're going to try and answer those, I think, offline now. Try and get back to everybody on those. I just want to kick around a few questions to the panel now. And the first one I have here is location of monitoring receivers in single frequency networks. I think everybody was indicating that it's wise to monitor not just at transmitter sites, but also external points. So any comments about how you select a location to do that monitoring? Hans?
Yeah, well, for what us concerns is actually we don't have monitor equipment in the transmitter sites, because probably it's the least important place where you are caring to be heard. I try, if possible, to place the transmitters, and currently we the receivers, and currently we are using transmitters from receivers from WordCast, which can also really monitor the SFN, so you can really see the different peaks of the transmitters. We try to put them in those places where we have a lot of transmitters basically arriving. So with one transmitter, with one receiver, excuse me, we can monitor a lot of transmitters. It depends, of course, if you have a suitable place. So really, we are very agnostic. We choose what we can basically get. So if we find a good place where we can place one of these receivers, we just take it. Of course.
What sort of place would you select there? Is it like the top of a building, or like a office block, or?
Yes, of course. No, I will go. We usually install dedicated band-free rooftop omnidirectional antennas in order to have as many signals available as possible. Mm-hmm. And then we set alarms on the levels, and of course, that's the most important part, really, on the timing. And of course, all this data goes into the network monitoring system also. So we'll have an alert if something will go out of SFN in a certain geographical area. And so we can retrace and try to figure out where the problem is. Because as I said also in my presentation, there is the risk of fake information from the transmitters, because if there is a software issue, if something hangs, maybe the transmitter will say that it's reading the correct timestamp and that everything is okay and the input is seamless, and it's not true. And he will say, yes, I'm okay, and it will not be true. And you will have a big problem in your single frequency network. So that's why you really need these receivers on field, because they give you a good feedback. Because or you use these receivers, or you rely on the listeners who then phone and complain about some problems in the coverage.
Yeah.
And of course, having a receiver is quicker and convenient.
Yeah, cool. Okay, another question, maybe this one for Christian. I saw that channel impulse response diagrams you were showing there. I'm just wondering what's the relative power of an out of guard interval signal that you can actually start to hear that interference is starting to make a difference?
That's a good question. I don't have the answer in decibel, but if we look at the neighboring adjacent channel interference, we then have 35 decibels, which will cause the problems. So I think that is the only answer I can give you now about 35 decibels. It has to be confirmed by somebody else. But to add up on your last question then, in Norway, where we have a lot of transmitters, over 1,000 of them, we rely on customers to report back the SFN problems. It's too expensive to put that equipment everywhere in Norway.
Yeah. Well, that's always an issue. Hans, you've got your hand up there.
I must say, we did some tests a couple of years ago. I don't have the slide here available, but it's interesting. The AutoSFN is very interesting because there are some receivers which, as soon as you move a signal 5 microseconds out of the guard interval, will get locked. And there are other receivers, also car receivers, which will stay locked even if you have it far out of the guard interval, as long as the other signal is strong enough. Car receivers in particular behave very differently. What we find is if the interfering signal is 15 dB or more below, let's say the threshold is about 15 dB. So it's very easy to interfere in existing another transmitter. So I think you have really to be very accurate in the timing and in the measurement of this. But as I said, the interesting part is not all receivers behave the same.
Yeah, okay, interesting. You know, it's obviously a very complex design problem to trying to make sure you get the optimum timing offset for your signals in a single frequency network environment. Are there any tools available to help design those those timing offsets, or is it more of a manual process? Anyone? Christian?
Yes, in the program we use to sort of calculate and do coverage maps, there is a feature where you can do an automatic. We use GearPlus from LS Telcom. So it's a feature there where you can actually do it, but we have not found that to be good enough. So it's still a lot of manual work, and it's when you put up the transmitters, you go out in the field and you have to adjust them. And every time you adjust something, you fix a problem somewhere, but you introduce a problem somewhere else.
Well, it just goes to show the value of field testing, which I always like to highlight. I've got one more little area to cover, and then I think we might start wrapping up. And that is, there's been a few questions about AI, artificial intelligence, and where that can be used. And I've heard, let's say, stories about using AI in monitoring systems to help learn what might fail when. as an example. Does anyone have any experience with this in this area, or any thoughts? Maybe maybe Kenny, how about you?
Yeah, I'll switch my video off just in case it kind of plays up again. But so in our network management system, actually, and that's actually the beauty of bringing back a lot of data from the systems that you manage and operate, is that you can then start to trend a lot of them. So we have a network management system from a company called Skyline, and we have some modules in there which are actually tracking and monitoring metrics along the way. So we're actually trying to develop profiles of transmitter systems and how they fail. So we're kind of looking at actually allowing some test cases where we maybe won't do any maintenance on certain transmitters, and we'll watch the failure modes of them. And then if we can model that, then we can actually try and predict when that happens. So there are certainly tools out there, and we're just going to starting to explore them. But that's certainly a strong area that we see, not just in helping to keep a higher availability and predict faults, but I think also try and drive some efficiencies in operations for organizations as well.
Okay, thank you for that. That's sounds like it's in early days at the moment. Hans, you've got something to add?
Yes, maybe from a very practical point of view, what we see, the failures we have in our network are mostly caused by, let's say, exceptional events. So power surges, lightning strikes, heat waves, phases in the electrical in the power system, which go because you have trees falling on the power lines, issues like this. And the other issues we see are software issues in a lot of modern transmitters, because a DAB transmitter is, okay, it has an RF part, but it has a lot of, let's say, it's a big PC with a lot of calculations we cannot predict the external events, so bad weather and heat and this stuff. And we really cannot also predict the software bugs. We see still, and that's the biggest problems we have really come from these two areas, not from, let's say, the natural usage of the transmitter, of the degradation of the fans and of the pallets, etc. So the big issues we have are really or external or software issues.
Yeah, okay. That's an interesting observation. It's external or a software. It's and the hardware is actually reasonably reliable. Yeah, interesting. Okay, I'm going to have one more question, and this one's for Jerome. I have a question from the floor. Says, can we use satellite link for program contribution to our remote stations? Jerome, would you like to address that one?
Yes. Yes. You can use satellites system for remote. It's possible. We use both. We use some satellite for local station, but and also a local fiber networks.
Okay, so the answer is definitely a yes there, and yeah. I know of other networks that use it also for not only contribution, for distribution as well. So satellites are often a quite economical source or solution for a one-to-many distribution system, just like DAB. Okay, we're just over time, so excuse me, I think we'll start the wrap-up process now, and I would just like to invite our sponsors to say a few words, I think in the same order our program. So that would be Ms. Bernie O'Neill from WorldDAB First. Bernie, would you like to make any closing remarks, please?
Yes, thank you, Les. World DAB has been extremely happy to organise this workshop with our partners, ABU and ASBU. We thank the whole team at ABU for the excellent event production. Thank you, Shri, Dr. Binbay, and all the team. And we also thank ASBU, Dr. Salhab, also for his valuable insights and assistance that he's given us. World DAB very much appreciates the collaboration that we have with you. We've also been truly delighted with the level of attendance and active participation we've seen over the past 3 days, and the number of attendees, I think, and the amount of questions we've seen you put forward are testament to the level of interest in DAB+ across the regions. So you've heard a range of presentations from larger network operators, such as Arqiva in the UK, TDF in France, and DAB Italia in Italy. And we've also heard a lot about the range of equipment solutions and technical support that is available from our World DAB members. So thank you to all our 15 experienced speakers from around the world for their great contributions. And finally, Les, thank you very much to you for expertly moderating this workshop. You've done a truly excellent job. I should say that Les chairs the World DAB Asia Pacific Technical Group, and he's one of the many experts that make up the total network of a World DAB who are here to support you on your DAB+ journey. So I'd say whatever stage you're at on that journey, I said at the start, our goal with this workshop was to empower you with the knowledge and support that will help you to deploy DAB+ in your country or region. And I hope that we succeeded in that goal, but that's up to you. Please do let us know what you thought of the workshop. And I'd like just to repeat also what I said in my opening remarks, that, you know, just to say that the support doesn't end with this workshop. You know, we offer ongoing support through our various groups and committees focusing on technical support. Hans Walter, who you heard from today, is the chair of a network, a spectrum and network implementation committee, and we've various groups working on cars and marketing, etc. So please do stay in touch, and we look forward to working with you and supporting you in the future. So until the next time, thank you.
Thanks very much, Bernie, for those kind words. Much appreciated. Okay, Dr. Wessel, would you like to have a few closing remarks, please?
Thank you. I totally agree with Bernie, and I'd like to thank to Bernie first of all, and World DAB team, all World DAB team, and excellent speakers. And I'd like to thank also to Dr. Adnan Shalhab and Arab States Broadcasting Union, our colleagues over there. And I'd like to thank all the speakers, 15 speakers that were excellent. And my maybe special thanks goes to this excellent number of participations, because this makes the event and workshop valuable, most valuable. These are the targets. So I think this international collaboration between organizations and between us is way to forward and gives an excellent platform to improve broadcasting overall, both regional and in global manner. So and my special thanks finally goes to Dr. Les, of course, wisely moderating this session and giving the presentations also. Thank you for that. Thank you, everyone, and looking forward to see much more collaborations for the future. Thank you all.
Thank you very much for those closing remarks. Good stuff. And finally, Dr. Adnan, would you like to have some closing remarks as well, please?
Yes, thank you, Dr. Les. I also feel happy with the results we achieved of conducting this training workshop on the Plus. I believe that we have got a lot of knowledge and experience from all. I would like to thank my colleagues from ABU and World DAB for excellent organization of this workshop. Special thanks to Dr. Les and other experts for valuable presentations and successful implementation. Finally, my thanks are communicated to all participants for the patient's interest and high level of interactivity. Just one maybe remark. I think very important for the Arab countries to finalize their regulation and legislation, as well as coordinate with all health stakeholders inside the country. So it helps the broadcasting companies to proceed in implementing the DAB+ in home, mobile, and vehicle services. Looking forward to increasing the various activities and continuing in productive cooperation with ABU and World DAB. Again, thank all.
Great stuff. Thank you very much, Dr. Adnan. Yes, and I'd like to highlight a few things as well. I think the interest in this workshop is outstanding. And one of the really outstanding things is the number of countries that our participants, the participants come from. And it really does show the level of interest is really peaking at the moment. You know, establishing DAB radio is a long process. I can't say it's a short process. It's, you know, broadcasting is always a long game. And we do have at World DAB an ebook on establishing DAB+ digital radio. I would encourage you to go and have a look at that. It might give you some additional guidance. On the Q&A, we've had a lot of questions. We haven't been able to answer them all. We will get to them, and we will send you some emails directly for those that we didn't manage to get to today. Our apologies, but time just runs out with these things. With so much interest, it's really, really good. I'd like to reiterate the thanks to all our speakers. We've had an excellent selection of presenters with, you know, deep knowledge and a willingness to share that knowledge with everybody to move it forward. So all across the globe, keep going. You'll get there eventually. So good stuff. I will now hand back to ABU for their final remarks on closing out this webinar. Again, thank you to the participants and thank you for your time.
Thank you, Les, and thank you all for this wonderful webinar series, 3-day webinar series. Really, every day the number of attendance going up, and we're really excited. Thanks to all the speakers. Again, I'm just reiterating from jointly from ABU, ASBU, and World DAB. As I have the final hit on the button to end the webinar, to end the workshop. So I will say thank you very much. So we will be there with you, and then of course our collaboration with ASBU and World DAB keeps going on for the next day as well. But before that, with ASBU, we have in October one big satellite workshop. We will certainly invite you, and then please join that workshop in October. Thank you very much. We'll see you somewhere again in the future. Okay, the workshop ends now. Thank you.
Bye-bye.
Bye-bye. Thank you.
Thank you, Les. Good work.
Thank you. Thank you.
Thank you, everybody.
Thanks, Les.
Thank you all.
Bye-bye for now.